Welcome to G Fun Facts Online. Today, we're taking an odyssey into the heart of our planet. We're going to uncover a geological spectacle of immense power, a supersonic volcanic event that forges a direct link between the searing depths of the Earth's mantle and the surface we walk on. This is the story of the Kimberlite Eruption, the planet's express elevator, whose precious cargo is the world's most coveted treasure, diamonds. These eruptions, which no human has ever witnessed, are not just volcanoes. They are a direct line to the planet's primordial past, carrying secrets of its formation from hundreds of kilometers below our feet. The journey begins long before the first flicker of life, deep within the primordial Earth. It's a common misconception that diamonds are born from the fiery magma that brings them to us. In reality, they are ancient passengers, created and stored in the planet's deep mantle for billions of years. Their vault is the safest, most stable place the Earth has to offer, the deep, thick roots of the Earth's oldest continental crust, known as Archean cratons. Think of these cratons as geological icebergs, rigid, ancient blocks of our planet's outer shell that have remained undeformed for over 2.5 billion years. They have deep keels that extend more than 200 kilometers down into the mantle, shielding their contents from the planet's turmoil. This is the perfect long-term storage facility for diamonds. Here, carbon crystals could form and wait for billions of years for their eventual, violent liberation. The formation of a diamond is a matter of precise physical chemistry. It can only happen within a specific range of high-pressure, high-temperature conditions, known as the diamond stability field. This region typically begins at depths of around 150 kilometers, or 93 miles. The pressures there exceed 4.5 gigapascals. That's over 44,000 times the atmospheric pressure at sea level, and temperatures hover between 901 and 400 degrees Celsius. Under these extreme conditions, carbon atoms, either from primordial sources or from ancient organic material dragged deep into the Earth, are forced into a dense, tightly bonded crystal lattice. This unique atomic arrangement is what gives diamond its unparalleled hardness and brilliance. Most gem-quality diamonds found today are between 1 and 3.5 billion years old, making them some of the oldest accessible materials on our planet. But diamonds have a common, less glamorous sibling, graphite. The lead in your pencil is made of the exact same carbon atoms as a diamond, just arranged differently. At the comparatively gentle pressures of the Earth's surface, graphite is the stable form of carbon. This means that, given enough time and heat under low-pressure conditions, a diamond will transform back into dull, flaky graphite. This presents a critical challenge. The journey from the diamond stability field must be incredibly fast. If the ascent is too slow, the precious gems would simply be erased, undoing billions of years of deep Earth alchemy. Only one natural process is fast and powerful enough to win this race against time: the Kimberlite Eruption. So what awakens this beast? The engine for this incredible journey is the Kimberlite magma itself, and its formation is a rare event tied to planet-shaping forces. It appears to be episodic, often happening during major geological upheavals, like the breakup of supercontinents. As a supercontinent like Pangaea stretches and rifts apart, the continental crust thins. This reduces the pressure on the hot rock below, which can lower its melting point and initiate the formation of magma. Another critical trigger is a mantle plume, a colossal upwelling of abnormally hot rock from the deep mantle. When a plume hits the base of a thick, rigid cratonic keel, it can cause widespread melting and trigger the creation of kimberlite magma. This magma is a strange and potent brew. It's extremely poor in silica but rich in magnesium. Its most crucial characteristic, however, is its immense load of dissolved gases, primarily carbon dioxide and water. At the immense pressures of the deep mantle, these gases are held within the magma. Water lowers the magma's viscosity, making it more fluid, while the CO2 provides the propulsive power. As the magma rises and pressure drops, the CO2 comes out of solution, forming gas bubbles. It is the explosive expansion of these gases that drives the eruption. Once a batch of this buoyant, volatile-rich magma forms, it begins a frantic, non-stop journey to the surface. It's not a leisurely flow. It's a high-speed transit through more than 150 kilometers of solid rock. The magma doesn't follow a pre-existing tube. It creates its own path, forcing its way up through weaknesses in the rock, forming a network of vertical cracks known as dikes. The pressure at the tip of the dike is immense, continuously fracturing the rock ahead. This magma is also an aggressive traveler. As it tears through the mantle at high speed, it rips fragments of the surrounding rock from the walls of the conduit. These captured rock fragments are called xenoliths, which means foreign rocks. They are an accidental cargo, but for scientists, they are an invaluable treasure. Because the kimberlite ascends so quickly, these xenoliths are perfectly preserved samples of the Earth's deep mantle, delivered directly to us. There are two key types. Peridotite xenoliths are fragments of the mantle wall rock itself, telling us about the composition of the upper mantle. And then there are eclogite xenoliths. Composed of striking red garnet and green pyroxene, many of these are believed to be remnants of ancient oceanic crust that was subducted deep into the mantle billions of years ago. The fact that some of these eclogites contain diamonds confirms that this recycled crust can be a source of diamond-forming carbon. The incredible speed of this ascent, estimated to be between 10 and 30 meters per second, or up to 80 miles per hour, is driven by the physics of decompression. As the magma shoots upward, the pressure drops dramatically. The dissolved CO2 begins to exhale violently, forming a rapidly expanding gas phase. This process, like uncorking a champagne bottle, drastically reduces the magma's density, making it even more buoyant and accelerating it further. Near the surface, this runaway gas expansion becomes the dominant force. After a journey of just hours or days, the volatile charged magma breaches the crust in a final, cataclysmic burst of energy. A kimberlite eruption is an event of unimaginable violence, a supersonic explosion that blasts a crater into the landscape. Geologists theorize about two main models for this power. A magmatic eruption is driven purely by the internal expansion of the magma's own gases. A phrenomagmatic eruption is when the explosive power is dramatically amplified by the hot magma instantly vaporizing groundwater, creating a massive steam explosion. Often it's a combination of both. The eruption creates a distinctive set of features. The initial blast excavates a bowl-shaped crater, surrounded by a ring of ejected material called a tuff ring. Below this lies the diatreme, the main, carrot-shaped pipe that can extend downwards for 1 to 2 kilometers. It's filled with a chaotic jumble of solidified kimberlite, mantle xenoliths, and country rock that's slumped back into the vent. For a glimpse of what this looks like, scientists turn to the Igwisi Hills in Tanzania. These are the youngest known kimberlites on Earth, erupting as recently as 10,000 years ago. Unlike the ancient eroded pipes we mine, the Igwisi volcanoes still preserve their surface features, providing a vital real-world laboratory for understanding these rare events. Once the fury subsides, what remains is the kimberlite pipe, a geologist's treasure map. Over millions of years, the soft upper layers erode away, often leaving a slight depression on the surface that conceals the diamond-bearing pipe below. But how do you find it? Diamonds themselves are incredibly rare, often just a few parts per million. Searching for them directly is like looking for a needle in a continent-sized haystack. Instead, prospectors search for kimberlite indicator minerals. These are minerals like specific types of pyrope garnet, chromite, and vibrant green chrome diopside. They form under the same high-pressure conditions as diamond, but are far more abundant. Erosion spreads these durable minerals across the landscape in a dispersal train. Geologists collect soil and stream sediment samples, and by following the trail of these indicator minerals upstream, they can pinpoint the hidden kimberlite pipe they came from. The global distribution of these pipes is not random. The vast majority are found exclusively within the Earth's ancient Archean cratons. Major kimberlite provinces are found in southern Africa, in the Siberian craton of Russia, and in the Slave Craton of northwestern Canada. This strict geographic control exists because only these ancient, thick cratons are deep enough to tap into the diamond stability field and old enough to have stored diamonds for billions of years. The discovery of these pipes has led to some of the most ambitious mining operations in history. The Big Hole in Kimberley, South Africa, was dug by miners with picks and shovels in the 1870s, creating what is claimed to be the largest hand-dug excavation in the world. It yielded immense wealth and led to the founding of De Beers. In Siberia, the Mirny mine is a staggering open pit, a spiral-shaped hole over 500 meters deep and 200 meters across. To operate in the extreme permafrost, where winter temperatures could shatter steel, Soviet engineers used jet engines to melt the frozen ground. More recently, the discovery of kimberlites in Canada's remote Northwest Territories in the 1990s set off a modern diamond rush. Mines like Diavik and Akati are marvels of engineering, operating on islands in frozen lakes, and they established Canada as a major diamond-producing nation. In the end, the legacy of Kimberlite Eruptions is twofold. They are the creators of the world's most enduring symbol of wealth and love, snatching diamonds from the jaws of thermodynamic decay and preserving them for us to find. But beyond the glittering allure of gems lies a deeper significance. Kimberlites are our most direct messengers from the deep earth. The cargo of xenoliths and xenocrysts they carry provides an unparalleled window into the composition and evolution of our planet's hidden mantle, a realm we can never visit. Each pipe is a geological probe, a time capsule bringing samples of the deep past to the present day. They tell a story written in fire and stone, a furious, high-speed journey that remains one of the most extreme and captivating phenomena in the natural world.